Good afternoon, everyone. Thank you, Piyush, for having me here. And thanks to Professor Gettu for initiating this, probably the first online workshop in this area. I think we are very happy and fortunate to be part of this. And this presentation, which I'm going to talk about, is mainly on the impact of chloride threshold and cover depth on service life of concrete structures. And this is mainly the accumulation of work by 4 of my PhD students, and also a little bit from my own master's thesis. So Jay Chandran, Sri Priya, Deepak, and Diana. So all the 4 works have been included in this. So the outline, I'm going to first talk a little bit about what is chloride-induced corrosion, how it happens, and what are the key parameters which we have to really focus on when we talk about estimating its service life. And then the one of the key parameter which we will be highlighting is chloride threshold, and how to test them in various systems, because today we have different type of steel reinforcement and different type of concretes. So we cannot really assume a single number for chloride threshold. And so we have seen that these threshold values keep changing as we change the system. So it's a steel cementitious system. It's not just a parameter only for steel. And then we will also show you how the synergy between the steels, these steel rebars, and the cementitious system which we use affect the estimated service life. And then finally, we'll also show you a little bit on how the cover depth plays a role in service life, and also show you some nomograms which have been developed, or is essentially the simple tools which can be used to do some preliminary assessment on service life. So this is the outline. So where do we see chloride-induced corrosion? Pretty much everywhere wherever you have access to chlorides, and it can be from a marine or coastal environment where you can see both airborne and soil-borne chlorides. And also if you have unauthorized use of saline water, groundwater, because if you say, what is the type of water that can be used for concrete, according to ACA, they say that as long as it is potable, and then also there are limitations on the amount of chloride that can be present in water. So if we cross those, if you don't follow those specifications, then you might have problem. And also we have seen many places where contamination of sand, like people use beach sand, knowingly or unknowingly, they use beach sand, and which results in premature corrosion, much earlier than we really designed the structures for. And then also I have heard cases where chemical admixtures are available, which has chlorides in it. So all these can lead to chloride-induced corrosion, which is really a dangerous scenario, and it affects the service life of structures significantly. So buildings, bridges, chemical plants, and any other structure, can be prone to this chloride-induced corrosion. So let's see what is chloride-induced corrosion. Now, whenever you talk about a corrosion cell, you have to think about an anode, a cathode, an electrolyte, and a metal. So here, the anode is the region which corrodes. So the anode is the region of the steel which is corroding. Cathode is the region of the steel which is helping the anode to corrode. And the metal itself play a role as a conductor or an electronic conductor between the anode and the cathode, and the cementitious system around provides the medium for the ionic conduction. So whenever we put steel in concrete, their passive film, because of the very high pH of the concrete, a small passive element, very thin but very dense and highly resistive passive film is formed on the steel surface. But when it comes in contact with chlorides or gets affected by carbonation, etc., this passive film can get damaged. And this damage can occur at any point, anywhere on the steel where you have high concentration of chlorides. Let me show you this. where you have high concentration. For example, imagine this is the case, and these thicker arrows kind of indicate that somehow the chlorides at the surface of the steel at that point was more than the chlorides at the remaining location. So this can kind of lead to a localized or an early corrosion at that point, and leading to eventually corrosion pits. Pitting corrosion is a typical form of corrosion which happens in case of chloride-induced corrosion. Now, what happens is, in terms of chemical reaction, what happens is you have, this is the anodic reaction or anodic half-cell reaction, which is happening at the anode site. And then the two electrons from there, the charge get transferred to a cathode site. On this image, I have drawn like this widely spaced anode and cathode, but in reality, it may not be like that. It will be very close to each other, but just for demonstration purpose, it is shown like this. Because especially when we talk about the highly resistive concretes which we have today, so we call it microcells, which form in an older type concrete where you have very low resistive concrete, you can have macro cells, which can also happen across between two rebars also. Okay, anyway, so what is the point on this slide is that when the chloride induced corrosion starts, the same chloride can participate in new chemical reactions, forming more and more rust. So what you see here is this Fe2 plus, it somehow first, let's say, start reacting with these chlorides, forming FeCl2, which in presence of moisture can produce HCl and FeOH2. So this is the rust which we are talking about. And then after that, this HCl will precipitate back into H plus and Cl minus. And this Cl minus is again available for this reaction here. So this keep on going until you have sufficient moisture or oxygen available in the system. So that's why we say like moisture and oxygen are essential for corrosion to continue. So if you can keep your structure free from oxygen and moisture, you're very good. It will not corrode that easily and probably not corrode. But that's very difficult to achieve. So for this slide, let's say this: as long as there are moisture and oxygen available, chlorides can continue to make more and more rust. And so what is that minimum amount of chloride required to initiate this corrosion? So what is that minimum amount of chloride? That is what we call as chloride threshold. So before going that, I'll show you also what is this pitting corrosion. So I mentioned that this pits form like in the previous slide. So you can see here, this rebar is almost animated to loose like that. But so that pit, in reality, it looks something like this. You can see here on a pre-stressing strand how the pit is formed. You can see very small pit, and it keeps growing and without really allowing the neighboring portions to corrode. So this is the danger. So because of this pit, the cross section of this particular reinforcement over here might be significantly less as compared to the cross section here. So you can have localized stress concentration. You can have stress concentration, which can lead to failure of the rebars or strands. So in the case of rebars also, you can see some pits forming here, but there are other regions which doesn't really corrode. So this is a typical form of corrosion due to chlorides, that is pitting corrosion. Now let's look at the service life, how the service life gets affected because of this chloride ingress and chloride induced corrosion. So here, this cross section I'm showing of a typical clear cover region. You can see this is the cover depth, and then the black circle here is the rebar, and then the blue arrow here indicates the penetration of chlorides through the concrete cover, and we are calling it diffusion coefficient or apparent diffusion coefficient, but because there are many other phenomena also. But for modeling purposes, we usually use this apparent diffusion coefficient, because that is the mostly the governing phenomenon of chloride ingress. So you have chloride surface, chloride at the surface of the concrete. We need to know how much is that, or in other words, the exposure condition. And then we need to know the cover depth. We need to know the diffusion coefficient of the chloride and the maturity function, or how the microstructure gets modified, especially with the case of SCMs. This also becomes very, very important. This value of M, it basically tells you that the diffusion coefficient after 28 days may not be the same as after, let's say, a couple of years. So we need to incorporate that effect also when we talk about modeling service life. And in this presentation today, we are going to focus on this chloride threshold of the steel cementitious system and how that influences the corrosion initiation time. And we are not focusing today on propagation phase, because the initiation time is the one which is really governing the overall service life. Okay, unless you go for a repair practice, etc. So typically, even worldwide, we say that corrosion propagation phase can be just about 6 to 10 years, whereas the corrosion initiation phase can be very, very long, depending on the type of steel and the type of concrete cover which we provide. So when we talk about service life, we have to look at the synergistic effect of all these parameters. It's not that you just talk about one parameter and then make the comparison. This concrete system is better than the other reinforced concrete system. We cannot do that. We have to look at the synergistic effect. So even if I'm showing you in the remaining presentation some chloride thresholds going down or decreasing, etc., you have to really think about the synergistic effect of that, because even if a chloride threshold is less, there may be other factors which help in enhancing the service life. That has to be taken into account. Now, there are various types of SCMs which we use. In the morning, we heard about various advantages of using SCM. So here is a plot which shows how the resistivity of the concrete can be different, how different it can be because of the change in the type of binders which we use. And this is a log scale you can see on this vertical. So there is a lot of difference between this box here and the OPC concrete which is here. So here the resistivity is in the range of 10 to 50 maybe, or maybe up to 30s. But when you talk about LC3, you are talking even more than 200 kiloohm centimeters. So there is a significant difference. And how this also helps in enhancing the service life. The increase in the resistivity can reduce the rate of corrosion, and at the same time that can also help in delaying the onset of corrosion. So we'll see how that is. So, but when you talk about chloride threshold test, we need a test method to test the chloride threshold. Now I'm going to show very briefly the different systems which I told earlier. We have, it's not only OPC concrete, we have now a lot of inhibitors being used. Earlier we developed a test called ACT, or accelerated chloride threshold, from my masters. But later on we found that there are a lot of inhibitors which is being used. So we could not, this test had to be modified to accommodate the presence of inhibitors. And later on we found that nowadays all the concretes which we talk about are highly resistive concrete system with fly ash, slag, silica fume, LC3 and low water binder with super plasticizers. So these combinations make it very highly resistive. And in such cases, these first two test methods here were not really functioning. So we had to modify with a simple test method, but a simple test specimen, but a relatively complex testing procedure. So then also this was further modified to assess the chloride threshold of pre-stressing strands and also for coated rebar. So I'm going to show you some results on this chloride threshold from these tests, especially the HRACT test or highly resistant ACT test for highly resistive systems. PS stands for pre-stressing, and then CS here stands for coated steel. So this is mainly work from my masters here, then my first PhD student Jay Chandran, Sri Priya, and then Diana and Deepak. So this is kind of, so this is how this HRACT test specimen looks like. On the left side, you can see the Lollipop type specimen. It's a very small cylinder with about 10 centimeter long steel rebar inside. and you can see, so this is how this test setup looks like. I'm not going to go more detail into this, but this is how the test setup is, and we can do electrochemical test. It means that you can detect the initiation of corrosion even before we can see the rust spot with naked eyes. So that's the beauty. Now, also when we talk about any of these electrochemical tests, when you are looking at repetitive test and continuous or wetting and drying type of exposure, and if you want to compare the electrochemical testing, then you have to make sure that all the tests are done with same humidity level, and which could be very high humidity to obtain conservative results. So this plot here shows how the chloride threshold value can vary as a function of humidity. So this very clearly shows that you have to have very high humidity so that you can get conservative test results. Okay, so in our testing also we maintain 90% plus relative humidity, and all the measurements were made at the same humidity level. That's very, very important. Otherwise, you get a lot of scatter in the data. So this is how the testing is done. You collect a lot of this corrosion rate measurements. You keep on doing the wetting and drying, cyclic wet dry exposure. And at the end of every wet exposure period of about 2 days, you take a corrosion rate measurement and then see when there is a statistical increase in the corrosion rate. Statistically, it has to be significant. Otherwise, we don't. Just some jump up, going up and down here doesn't mean that there is a corrosion initiation. It has to be statistically significant. So 3 times the sigma of the corrosion data, stable corrosion data is used for this. So finally, we tested many specimens. I'm going to show you this. So this is how a typical graph will look. You can see that very low corrosion rate, and suddenly there is an increase. And at that time, what we do is we open the specimen or autopsy the specimen, and then at the steel surface, you can see the rust formation here. So that is an indication of corrosion. So at that point itself, you collect the mortar powder and then do a chemical test. And this test, the chemical test, and then determine the chloride concentration in that powder. And then we define that as the chloride threshold. So in the remaining slides, I'm going to show you the chloride threshold for various systems determined like this. And beauty of this test is we can determine the chloride threshold in about 3 to 4 months. If your system is very, very good, it will take longer time. But so this is, for sure, chloride threshold of various steel systems. This is from my master's, and where you can see that chloride threshold can significantly increase with the use of stainless steel or even some corrosion resistant steel, microcomposite steel, you can see here. So however, in that study, we looked at only the effect of steel, but cementitious system can also very much influence the chloride threshold value. And one such variation which can be made to the cementitious system is the use of corrosion inhibitors, which is widely used in today's market. And these are very promising, material or, admixtures, which can be mixed with concrete, and that will form a very thin, or it will enhance the passive film which is formed on the steel surface, which will then resist the corrosion for much longer time, or you need higher amount of chlorides to initiate corrosion. These are some of the products which are available. Many companies are producing this corrosion inhibitors. I put this slide because there's a lot of request on these type of products. So many other equivalent products also exist, but make sure they are all in bipolar in nature. What it means is that some inhibitors, they control only the anodic reaction, and some other control only the cathodic reaction. But what we need is, we need to control both the anodic and the cathodic reactions. So this is very, very important to have a bipolar corrosion inhibitor or a mixed corrosion inhibitor. So how is the effect of this on chloride threshold? So you can see here, without an inhibitor, the chloride threshold, if it is about 1, and then if you have an inhibitor, it is about 2. Basically, it's showing that there is a the chloride threshold can increase by twice or 2 times increase. And if that is this was tested using one of the earlier test procedure, and then what we found is if you have that much increase in chloride threshold for a particular system with a 0.45 water cement ratio and a cover depth of 50 millimeter with an OPC concrete, then you can have 3 times, or let's say 2 to 3 times increase in the service life. So it's very promising. So we actually tested more, perform more tests on corrosion inhibitors. And in between, I'll also tell you something about how the binders can influence the chloride threshold. How the binders. So here in this study, we are showing the effect of PPC or fly ash on the binder, on the chloride threshold. You can see there is a reduction in the chloride threshold. It's from, if it's an OPC case, which is about, let's say 0.4 to 5 chloride threshold. And if the binder is changed to PPC, the chloride threshold decreases without any corrosion inhibitor dosage. But is it something to worry about? No, because even though the chloride threshold is decreasing, when we use fly ash concrete, the diffusion coefficient also decreases significantly, which still gives you a significant increase in the service life. So here in the case of OPC, if it is about 50 years, still in the case of PPC, you can get 90 years. So these are all case studies which we do with assumptions. So for different type of steel concrete systems, you will have to do these kind of studies or estimates and then come up with your own conclusions. But just to show you how impactful these SCMs can be on service life. And now, if this CI or corrosion inhibiting admixtures are used, we can still increase the chloride threshold of PPC itself. So this reduction which happened because of the use of PPC can be compensated by using the corrosion inhibiting admixtures. So if you use a 1% of corrosion inhibiting admixture, you can just get back whatever the chloride threshold was reduced. I mean, whatever the reduction happened, it can be regained or compensated by the use of CIAs. So or inhibitors. So you can see here also with the incorporation of both fly ash and corrosion inhibiting admixtures, the blue bar shows you can really get 120 years of life if required. So definitely the use of SCMs and the use of inhibitors can definitely enhance the service life significantly. That's the message. Now, one point to tell when you talk about corrosion inhibiting admixtures is that they do not function when the water cement ratio is very, very high. So don't waste money in using corrosion inhibiting admixtures if you cannot ensure quality use of water at site and if the water cement ratio is not very high, if not very low. So definitely this is very useful product for systems with low water cement ratio and SCMs. Now, there are also tools available to estimate service life. One of the widely used tool is Life 365, which is freely available. You can download freely from the website. This is the various associations which help in making this tool, and it was with the support of ACI and NIST in the US, who started formulating this consortium and then developed this tool. So I'm going to show you a brief on how this tool can be used. The bridge, see the effect of water cement ratio. If you want to show, look at column row 1 and row 4 with the change reducing the water cement ratio from 0.6 to 0.4. The service life can be significantly increased from 60 to 80 years. So the reason I'm missing that column here. So that's the outcome. You can significantly increase the service life. So let me show you this effect on the use of fly ash and LC3. LC3 is a new binder, a relatively new binder. So this we found that the chloride threshold of the system is very low as compared to OPC system. However, when we look at the synergy of this, we can very clearly see that the service life is still going to be high. I'm going to show you that in the next slide. So we did a case study on this. You can see where we took a typical pillar or pier of a metro elevated metro, and then we looked at the actual cover depth which was used. We also got some field information from the actual test on this cover concrete, looking at the diffusion coefficient of that concrete, etc. And all used the chloride threshold values, which I showed in the previous slide. This was these 3 chloride threshold values. And then we found that the service life can be significantly increased if you have, if you use this special SEMs or LC3 and fly ash based system, you can have significantly high service life. Now, for the epoxy coated system, also you see very significant reduction in chloride threshold, but the point is that it is very low, and we should not be using this type of steel if you cannot make sure that the steel surface is not damaged or degraded. Okay, but unfortunately, this is the case in most cities. We'll allow these rebars to get scratched, like you see on the photograph on the right side. Now, this is the effect of that on service life. If you have uncoated rebar, you will see the service life is about 100 years. In such a case, if you use a damaged epoxy coated rebar or an epoxy coated rebar which is exposed to sunlight severely, then the service life decreases to about even 50 years. That is 50% reduction. That is a significant reduction in the service life. Now, another system which we looked at is prestressed concrete, where also we have to look at, most literature shows the effect of, do not show the effect of stress on the chloride threshold. So when you look at the, we developed a test and we looked at the chloride threshold with the presence of stress, and we found that there is 50% reduction in the chloride threshold value. However, also when you use the fly ash, there is the reduction is not that significant, okay, in the chloride threshold. So again, it tells the point that we must use SCMs when we talk about prestressed concrete. Why I'm saying this is, still there is a lot of hesitation in using fly ash and slag in prestressed concrete systems. So it's a high time that we should change this. We have to use SCMs in those type of concrete systems also. Now, so this is the effect. The blue curves here, it shows very clearly that if you use fly ash based systems in prestressed concrete, I mean, again, this 20 years is just a case study which we are showing. If an average, if you can get 20 years with the fly ash based system, if you are actually using OPC based system, you will get only about half of it. So these are the important points, like, we have to use SCMs in prestressed concrete also. Another important parameter is cover depth. So
Dr.
this
Pillai,
just to show you.
Sorry to interrupt. Can you wind up in a few minutes?
Yeah, I'll just, this is the last slide, couple of slides. So 30 millimeter, if you have a cover depth of 30 millimeter, 40 and 50, you can see that the the service life can increase with about 65% by every 10 millimeter cover increase. So this is very important to tell, because we worry about many other things, but at the site we don't really ensure the proper cover depth. So if you have really interest in enhancing service life, cover depth is very, very crucial. Okay, so, and also don't use cover depth which are brick pieces or plastic products. They don't really work well. Use a concrete which is of similar type. That's enough for cover depth. And you can enforce performance specification. After the concreting is done, you tell the contractor that you will come and measure cover depth. That will really ensure. Now, nomograms are also developed here. You can use this as a very simple tool to tell what should be the target diffusion coefficient for the concrete. So idea here is, first, in a structural office, you will decide what is the cover depth and what is the acceptable failure probability of failure. Then you talk about what is the type of, or decide what are the type of cementitious binders to be used. And then you look at what is the diffusion coefficient, which can be set as a target diffusion coefficient to achieve a particular design life. Okay, so my point here is, you have to look at all the synergistic effect of all the parameters, and then you have to specify MX-DY mix. That means nowadays we may specify only a compressive strength based concretes, but we need to start specifying compressive strength and a durability parameter as a concrete which we can specify. I think in future we will start seeing this, because durability is definitely governed by the diffusion coefficient of the concrete and also the chloride threshold, and covered that. But when you talk about what type of concrete to be used, we have to say that it's not only strength but also durability. So the one word, if you want to remember for today, is I would say that let's start specifying MX-DY concrete, or a parameter which influences which represents the type of which represents the diffusion coefficient, which is the target diffusion coefficient. So to summarize, we developed some ACT test methods, and we found that positive effects of corrosion inhibitors and SEMs, when you use, we have to look at the synergistic effects. Not only it's their effect on the chloride threshold, but also on the diffusion coefficient. And epoxy coated rebars can be used only if they are undamaged. And stress on prestressing steel must be considered while addressing service life. And use SEMs in prestressed concrete. And nomograms can also be used, and ensuring design cover depth is very, very important. So let's use SEMs and specify MX-DY concrete to achieve durability. I think with that I will stop. I think I started 5 minutes late. So
okay, thank you for a detailed talk, very informative talk. There are a lot of questions. I can only take few questions in the interest of time. I will start with, can you comment on a size effect of for the chloride threshold value and its scatter going from mortar to lab concrete to full scale specimens?
Definitely, I think there is also literature on this size effect, and that's one of the reasons why we moved from my first test specimens, which had about 1 centimeter long specimen. Now we are using about 5 centimeter long exposed region. So when you have larger space or size effect, if you are talking about, are you talking about the length of the steel or the other factors?
I think the question is from the size, small size to large size of concrete.
Yeah, with the larger the size, you will find that chloride threshold is also going to be higher.
Okay.
Because it's again essentially the probabilistic function effects come into the picture.
Okay. Another question. Table 7 of IS 456 gives the permissible value of total acid soluble chlorides in RCC as 0.6 kilogram per cubic meter. Can we expect this to be lower for concretes having lower pH? Or
see, that is permissible limit for the initial, like it's the initial chloride content. It is nothing to do with the chloride threshold. So I think we can still go with those kind of limits. That is fine, because it's essentially the chloride threshold. And when we use SEMs, you have anyway very low diffusion coefficient, which will have positive effect on service life anyways.
Okay. One other question. Some tests say that the little corrosion is also helpful with respect to bond with the concrete. Is it true?
Can you say that again? I couldn't hear.
Some tests say that the little corrosion is helpful with respect to the bond with the concrete.
Good that you raised this point.
Is this true? That's the question.
Yeah, it is true up to about 1%. But very recently we found that most of these coated rebars which we use, it's also reported widely in literature, when there is a very little corrosion, when you have coated rebars in place, it affects the bond strength significantly. So that concept of having a little bit of corrosion enhances the bond strength, it's only valid for uncoated rebars. It's not valid for coated rebars. For coated rebars, you see drastic change, like about 50 to 70% of reduction in the bond strength as soon as the corrosion starts.
Okay. Final question. Protective coating in reinforcement reduces bond between concrete and steel. How can we rectify this problem? And which corrosion protection method is cost effective?
See, the corrosion protection method in such, I would say go with the very good concrete. That's the best thing, because otherwise it's cathodic protection, but there are also issues associated with applying cathodic protection on coated steel. It's still an area to be researched out. But for now, if you really have to use coated rebars for various reasons, you better go with the very, very good quality concrete. Ensure, put extra inspectors at site to ensure quality of concrete and cover depth. Otherwise, we will see a lot of problems with these coated rebar systems.
Okay. Thanks so much, Dr. Pillai, for very informative talk and taking all the questions. As again, like audience can email him for, if some of their questions have not been answered. That's always the case. Thanks so much.
Thank you. Thank you.